To go. Okay, last time we have been, so I'll just say that we're maybe not going to finish chapter 13 today. We've spent a lot of time dealing with theory and general examples to try to set a framework that's going to help you understand all of the details. It's going to be worth the time. You're going to see that we'll be able to go through the details a whole lot quicker once you understand the background, the mechanism. That being said, if you're done with Study Guide 13, Chapter 13 today, you're good to go. We're probably going to take maybe 10, 15, 20 minutes next time on Chapter 13, so we're not going to get all there today. That's okay. I built some flexibility into the schedule, so we'll be fine. And I'll try to keep you updated with semi-regular emails letting you know where we are and where we got to in each lecture. Okay, so last time we were dealing with this question of what is the nucleophile, how good is the leaving group relative to a negatively charged oxygen? The fate of the tetrahedral intermediate, we could call that. We dealt with a situation where the leaving group, the Y group, was quite good relative to a negatively charged oxygen. Recall, to make this comparison, you simply draw the leaving group after it's left and compare its stability, its goodness as a leaving group, versus the negatively charged oxygen in the tetrahedral intermediate, right? And the issue there is compare pKa's of conjugate acids, right, if you're a little bit confused on that. Chloro is a much better leaving group than O minus, and so it stands to reason that O minus should be able to kick down and kick off the leaving group. O minus is a good enough kicker-offer to kick off the Cl minus leaving group. We expect this reaction to be very favorable in the forward direction. Another example was, what if the Y group is methoxide, such that if the electrons on the negatively charged oxygen kick down, what would leave is OMe minus. And the comparison there would tell you, well, the conjugate acid of methoxide is methanol, which has a pKa of 16. That's about as reactive. Methoxide is about as reactive as the negatively charged oxygen in the tetrahedral intermediate. So we predict this reaction step where methoxide leaves to be totally reasonable. It stands to reason that one negatively charged oxygen should be able to generate another, but we predict that the equilibrium constant here would be much less favorable, that this reaction might be reversible. Another way of saying that is it's probably pretty reasonable for methoxy to hop back on and attack the pi star to regenerate that tetrahedral intermediate. Being able to tell whether a reaction should be really favorable in the forward direction or reasonable but perhaps reversible is pretty useful. Finally, we had an example where, no way ever is that going to happen. And that is if the so-called Y group were a hydride, H minus, if it left, it would be H minus, right? Can a negatively charged oxygen kick off H minus? Comparison of pKa's of conjugate acid tells you never. That reaction's not favorable at all. Yeah?
In the case that the pKa's are pretty close and it's somewhat reversible, if the leaving group is really big, would it be more preferable as a leaving group just because it would be harder?
Sure, it's a good question. If pKa's if you're in a situation like this where it's reasonable and reversible, could you think of ways to bias the reaction so it would be even more favorable? Like if the leaving group was huge and you were reducing some kind of steric strain in the tetrahedral intermediate, sure. I can't think of a specific example of that, but it's an interesting idea. Okay, so this is going to help us out a lot with deciding what's going to happen next in a reaction. Will we get a product like this where the leaving group is left, or will we be stuck at this tetrahedral intermediate stage because we simply haven't got a good leaving group? That's really useful. That's going to help you have to memorize less. Now, there's one area that we should have talked about probably before this, but that we didn't, and that is to examine the efficiency of nucleophilic attack. And it turns out we're going to ask a very similar question with deciding whether that nucleophilic attack step is going to work or not. I'm referring to this step where the nucleophile attacks the pi star to get a tetrahedral intermediate. We've talked about that mechanistically, but we haven't yet dealt with the issue of how favorable is that reaction. And the basic question we're going to ask is very similar to the question we asked for the leaving groups, and that is basically how reactive is the nucleophile relative to the negatively charged oxygen in the tetrahedral intermediate. And I'm not sure how to write that, so maybe I'll just write it like that, and you can understand that I mean the negatively charged oxygen in the tetrahedral intermediate. In other words, I'm going to be asking, should this nucleophile be able to generate this kind of intermediate? And we'll have the same judgment call. We'll compare the reactivity of the nucleophile versus the negatively charged oxygen. So let's think of a few sort of examples for this. Let's let the nucleophile be OH minus. And then at this stage, it doesn't even matter what the Y group is, so we'll just be as generally as we possibly can. We're going to actually draw the mechanism, because the mechanism gives us the instructions for that tetrahedral intermediate. Here's the nucleophile having attached on, and there's the tetrahedral intermediate. Fine, we can highlight the Y group. And we're asking, is this step reasonable? And to do that, again, you can draw the conjugate acid of the nucleophile and remember or look up its pKa. For water, it's around 16. You can draw the conjugate acid of the kicker offer. It's just an alcohol, also pKa 16. So we expect this to be pretty reasonable, but probably reversible. Right? Seems likely possible for OH minus to attack the carbonyl carbon, but probably it's reasonable for it to go backwards and OH minus to be kicked off. Do you see how that's sort of the same question as we asked about the leaving group? Can the nucleophile attack? Could it be kicked right back off? Is basically the same thing as asking, could the leaving group be kicked off? Could the leaving group come back in and attack? Same kind of comparison. Okay, let's change it up just a little bit. What if I'm going to introduce something here. I didn't do this in the 9 o'clock hour, so maybe this is a bad idea. I'm going to introduce an organometallic reagent. This is called an organolithium reagent. Some of you have already read about this. It's not exactly like this, but you can think of it as an alkyl group with a negative charge on it. So let's just say we're using, this is a terrible idea, but methyl lithium. CH3 minus, basically, as a nucleophile. And so we'll do examples of this, probably not even today. This is sort of why I'm getting ahead of myself. But let's imagine using CH3 minus as a nucleophile. So you can think of this as though it's just this. It's not, but we can pretend like it is. I'm going to put it in quotes. So that, anyway, let's draw what the product would be. Lone pairs or electrons in the carbon-lithium bond leave with carbon and attack the carbonyl carbon to give us a tetrahedral intermediate. We're asking, is that reasonable, and is it possibly reversible? Again, if you are struggling to reason the way through this, draw the conjugate acid of what your nucleophile is, look up its pKa, in this case it's 50, do the same for the kicker offer in the tetrahedral intermediate, which we've done before, and that pKa is 16. Oh yeah, it's totally fine for that nucleophile to attack the carbonyl carbon. That's super reactive relative to the negatively charged intermediate. And probably that equilibrium constant is super favorable, way, way more than 1. Probably even that step is irreversible. You would never in a gazillion years propose that OH minus should be able to kick off CH3 minus, right? That sort of make sense? Okay. Let's do one where the nucleophile maybe doesn't look like it should be strong enough to attack. So let's just use water instead of OH minus. We can go ahead and draw the mechanism, but remember we're asking the question, is this step reasonable or not? Here's our tetrahedral intermediate. The Y group, what used to be our nucleophile, and the negatively charged oxygen. And then we ask ourselves again, is the nucleophile reactive enough to generate that tetrahedral intermediate? And you'll build up intuition so you won't have to do this anymore. But if we draw the conjugate acid of the nucleophile, that's just hydronium, pKa minus 2. Compare that to the pKa of the conjugate acid of our kicker offer oxygen, which is 16, and you can see, yeah, that water is not reactive enough to attack, okay? So, we're gonna, go ahead.
What's the pKa of OH minus?
OH minus, so I assume by saying pKa of OH minus, you mean the pKa of its conjugate acid? That's the pKa of water, that's 16. Yeah, pKa of water and alcohols is the same, basically. All right, now it turns out if you have a nucleophile that's not strong enough to attack directly, you do have options. You just sometimes might need catalysis to make the reaction happen. So here is a preview of what acid catalysis can do to this situation where we want to use water as a nucleophile. Because we're going to do that in this chapter, but in chapter 14 we will all the time. We'll use things like water or alcohols as nucleophiles all the time. We'll use acid catalysis when our nucleophile is not strong enough to attack directly. And what happens here is you start with your carbonyl compound. You add an acid. We already learned that if carbonyls are nucleophiles, it's the lone pairs on the carbonyl oxygen that do the attacking. So the acid will protonate the carbonyl oxygen to give you this positively charged oxonium ion, which is now activated for reasons that we might talk about later. Probably doesn't matter for today. But what I want you to focus on is what intermediate forms when water attacks that positively charged oxonium ion. Let's draw that out. And let's think about the comparison now. Neutral nucleophile. The kicker offer group here is now a neutral oxygen. Do you see how that's much more reasonable? Before, above, we were proposing that a neutral nucleophile should generate a negatively charged oxygen intermediate, but if we protonate the carbonyl compound first, then it's not negatively charged anymore. So acid catalysis can make it possible for weaker nucleophiles to attack carbonyl compounds. That's something we'll pick up again in chapter 14, but that I wanted to provide you a brief preview of. Okay, questions about that? We've done fate of the tetrahedral intermediate. We've done nucleophilic attack. This now allows us to describe two basic mechanisms that are going to summarize everything that you will learn in these first few chapters of OCHEM. Nucleophilic addition to the carbonyl is what happens when your nucleophile is good enough to attack, but the leaving group is not good enough to leave. So a classic, so let me just show you that mechanism. That's going to involve nucleophile attacking the carbonyl carbon to give you a tetrahedral intermediate. At that stage, the leaving group is not good enough to leave, so there you are stuck until usually, now, and we're going to call this now, instead of a tetrahedral intermediate, we'll call it a tetrahedral product. We're sort of stuck here because Y is not a good leaving group, so it's not going to leave. Your nucleophile is added on. You're sort of stuck until what I will call aqueous workup, and this is where it's a phase that happens after most organic reactions where you wash the organic solvent with water. You add water in the two phases. The organic solvent is not miscible with water in a lot of cases, so you shake them up together, the water separates out, you throw away the water. But the effect of what happens is that the water protonates the things that are negatively charged, like the oxygen in the tetrahedral intermediate. And the product that you get from that looks like this. And if you pay attention, what got added to our starting carbonyl was the nucleophile and the hydrogen. And people will sometimes call that a 1,2 addition product because the nucleophile and the hydrogen that got added are on adjacent atoms. That's what happens when Y is a terrible leaving group. In contrast, if Y is a good leaving group, you can expect what's called nucleophilic acyl substitution to happen. So nucleophilic acyl substitution is what happens when the nucleophile is good enough to attack, and the Y group is good enough to leave. So here, lone pairs attack the carbonyl carbon, we get the tetrahedral intermediate, but once we're there, because the Y group is a good enough group to leave, electrons on the negatively charged oxygen kick down and leaving group leaves, and we end up with this product. It is called a substitution product because the nucleophile occupies the place where the leaving group once was. Here's the negatively charged kicker-offer, here's the leaving group leaving, there's the nucleophile. So that's why it's called a substitution reaction. Nucleophilic, because the thing that gets substituted in is the nucleophile. Acyl, what does that word mean? Acyl refers to this group in the starting material and in the product. A carbonyl carbon and oxygen functional group bound to some other group like an R group. Okay, that's an acyl group. Nucleophilic acyl substitution. Notice that nucleophilic acyl substitution involves an addition step, which is then followed by an elimination step. One really important point for nucleophilic acyl substitution is that it always goes through this type mechanism. You will be tempted, based on some stuff that you learned probably in 351, you will be tempted to do an SN2 mechanism. You're going to want to show it like that. When you draw it like that, I'm going to just, because zero points. Is that menacing enough to you? That is an incorrect mechanism. The reason it's incorrect is if you draw it this way, you are proposing that the nucleophile attacks the carbon chloride antibonding orbital. But that's not the lowest energy empty orbital in the molecule. The lowest energy empty orbital in the molecule, the LUMO, is the pi star. The nucleophile must attack the pi star, and you must get a tetrahedral intermediate. And there is all kinds of excellent experimental evidence that this is the case. Yes?
So then after that, the next step would be the lone pair on oxygen attacking the anti-sigma bond.
Right, so in the elimination step, you can think of this as lone pair on the oxygen dumps its electron density into the sigma star antibonding orbital with the leaving group. Yes. Okay. So I can guarantee you that on your first exam, there's going to be a question about mechanism, which of these steps is reasonable. for a nucleophilic acyl substitution reaction. And at least some of the answers that are not good are going to look like this. And in the fog of war, you're going to look at that and say, that looks good, because it's simple and it puts the bonds in the right place. Do not be deceived. That doesn't happen. Okay? I am evil, but I disclose my evil tricks ahead of time in many cases. Follow-up question. In which cases do I not disclose my evil tricks? I don't know. Go ahead.
So it's called a nucleophilic acyl substitution even though it's an elimination step.
It's both addition, it's stepwise addition and elimination. So overall, those two addition and eliminations are nucleophilic acyl substitution. It's a two-step sequence. Step 1 is addition, step 2 is elimination. Yep? Yes?
So would it be considered an SN1 reaction then?
Would it be considered an SN1 reaction? No. But the real question that you might have is, what are the kinetics of this reaction? Which step is the slow step? And that's a great question that I don't have a general answer to. Usually it's steps that break bonds that are the slow steps. So the first step, though, makes a bond and breaks a bond. So it's difficult to say, and it depends on the situation. And once you start adding in catalysts, that can change the story. So the reason that we haven't drawn an energy diagram for this is probably because it wouldn't be general enough to be useful. Yeah. Okay, what else? Yeah.
With this kind of being stepwise, stepwise reaction, several steps, if the first step with the nucleophilic attack was reasonable but reversible, and then the second step with the leaving group being a very good leaving group, would it be sufficient to have just that second step being a really good leaving group to have a good yield on the reaction?
Yeah, so we're talking theoretical. It'll be helpful to actually get down to specifics to answer this question. But the idea is, what if this first step is reversible, but the second step you predict to be really favorable? Is that good enough? And the answer is yes. If the leaving group's really good, then even if the first step is not that favorable by Le Chatelier's principle, that pulls you towards products. Yep. And that's why we've paused to rank. That's why we started our work this semester sort of learning to rank carbonyl compounds in terms of reactivity based on leaving group. And we'll have more to say about that in a little bit. So for the rest of chapter 13, we're going to be talking about nucleophiles that are very strong and are good enough to attack directly. Chapter 13 focuses on hydrogen-based nucleophiles and on carbon-based nucleophiles. What we'll have time for today is probably the hydrogen-based nucleophiles. If we're lucky, we may get to some of the carbon-based nucleophiles. For hydrogen-based nucleophiles, what do I mean? Well, if I want to use H- as my nucleophile, I got a big problem, and that is I can buy sodium hydride, Na+, H-, but it's not particularly soluble in organic solvent. And why do things need to be soluble? Well, they have to dissolve and mix together so the hydride can even get close to the carbonyl carbon. So something like sodium hydride is a non-starter. H- is, as I've said, a terrible leaving group. It's also not very soluble, so it's a terrible nucleophile. So you need something to deliver the hydride to its location. You need a hydride delivery system. You guys are all probably too young to have watched Parks and Rec, maybe not, but Chris Pratt's character, yeah, okay. Chris Pratt's character, Andy Dwyer, is once explaining to Ron Swanson about this burrito called the Meat Tornado, and Ron says, "You had me at Meat Tornado," and in his enthusiasm, Ron explains, it's like a whole new meat delivery system. It's like, yeah, Ron, tacos have existed forever, but he had never considered them. Well, what we need here is a hydride delivery system. We need something to hold on to the hydride, make it soluble in organic solvent, and then deliver it to the appropriate location. So we're going to introduce a couple new hydride delivery reagents today. One is called sodium borohydride. Sodium is simply the counter ion. The real business end of the molecule is the boron, and the boron is bonded to 4 hydrogens. It's sp3 hybridized, and you would draw a negative formal charge on the boron. And you could be forgiven for saying the negative formal charge on the boron means the boron is especially electron rich. You would be wrong, because boron is less electronegative than hydrogen. Meaning that actually, if you do the calculations, most of that negative charge is out on the 4 hydrogens. In other words, the hydrogens in sodium borohydride are nucleophilic. But the hydride isn't on its own, so you don't have to worry about the solubility problem. BH4 is a hydride carrier. It can carry the hydride to where it needs to be and then let go of it and have it do what it needs to do. There is a second reagent called lithium aluminum hydride, which is like the stressed out cousin of sodium borohydride. It's way more reactive, and the reason it's way more reactive than sodium borohydride is that aluminum is even less electronegative than boron, meaning even more of the negative charge is going to be out on the hydrides for lithium aluminum hydride. So lithium aluminum hydride is more reactive, it's also more expensive. Sodium borohydride is less reactive but less expensive, so you often use it when you can get away with it. One advantage of sodium borohydride is because it's less reactive, protic solvents are okay. You may have learned about that term in 351. A protic solvent is a solvent that has a hydrogen on it that might be removable because of its pKa. You can use alcohols as solvents for sodium borohydride. You can't for lithium aluminum hydride. You have to use other types of solvents. Yeah?
So one of them be better for like SM1, one of them be better for SM2?
Would one of them be better for different types of situations? It will depend on 2 things, well, several considerations. First, cost. Second, what kind of solvent do you want to use? And third, perhaps most importantly, how's it going to react with the carbonyl compound that you're dealing with? So the other thing we need to do before moving on from these hydride delivery reagents is to just recall what we've learned about carbonyl compound reactivity. We've ranked carbonyl compounds from most reactive to least reactive, and we've had a few different categories. On top are all of the ones that either have an excellent leaving group or have something that's not a particularly good electron donor. So at the top of our list, you have things like aldehydes, ketones, acid chlorides, and hydrides. I'm going to put thioesters up here. And there are some other biological compounds that I'm not putting on the list yet, but we will revisit. These are all molecules with sort of either really good leaving groups or really cruddy electron donors like hydride or methyl. Things where you can expect a big buildup of positive charge on the carbonyl carbon, or in these cases, super good leaving groups that are happy to leave that will drive a reaction forward. A little bit further down the list, you've got esters. As you've seen, the OH minus is a perfectly good kicker-offer, but not as good as kick-off-E, rather. The negatively charged oxygen in the tetrahedral intermediate can kick off OR minus as a leaving group, but it's not as good of a leaving group as Cl minus. Esters are less reactive than aldehydes, though. Why? Because the oxygen is a good electron donor. A little bit further down the list would be amides in their varieties, and the reason the amide is lower than the ester is because the NH2 minus group is a terrible leaving group, but the nitrogen's a good electron donor. At the bottom of the list, and this is something I didn't say in the 9 o'clock hour because it didn't come up, is the conjugate base of a carboxylic acid. The carboxylate is a terrible electrophile. And the reason it's a terrible electrophile is because it's already negatively charged. And lone pairs on that oxygen donate into the carbonyl carbon via resonance and make it very much not electron poor. So it's helpful to recall this because we're going to use this ranking of carbonyl compound reactivity to explain some of the results of what I'm going to talk about. What I want to do now is show you the reaction of some of the most reactive carbonyl compounds with some of these hydride delivery reagents. Okay, questions before we do that?
What's the least?
Least reactive was this carboxylate, the conjugate base of a carboxylic acid. I'm not putting carboxylic acids on this list because carboxylic acids have an acidic proton on them, which is going to be the first thing that gets involved even before a nucleophile were to attack the pi star. So we'll deal with carboxylic acids, but we're going to deal with that later. Yeah?
Aside from just like the ranking, kind of like memorizing it, can you like use like pKa to tell that?
Yep, so aside from memorizing, two things. First, pKa of the conjugate acid of the leaving group would get you this ranking. Second, remembering the issue of electron donation. And knowing that hydride and CH3 are not as good electron donors. Why? Because they don't have lone pairs.
So if you have bad electron donation,
Highly electrophilic, yep. I saw a hand in the front, or did I? Do you have a question? Yeah.
Yeah, so you said that the best or the most reactive are because they have good leaving groups and because they're poor electron donors, is that right? Or
It's sort of an or. So some of the reactive ones have excellent leaving groups. The excellent leaving groups in general are poor electron donors. Aldehydes and ketones here, those are not good leaving groups at all, but they're also really, really terrible electron donors, and that makes the carbonyl carbon really electron poor. Yep. Okay, good. Well, let's do some actual chemistry. So let's draw an aldehyde, and let's react it with sodium borohydride. And the way you draw this mechanism is you draw the BH4 minus anion like this, and then you show the H minus being delivered to the carbonyl carbon like that. Effectively, what's happening is you're breaking the boron hydrogen bond at the same time as hydride is attacking the carbonyl carbon, and then you're breaking the pi star. Or you're dumping electrons into the pi star, breaking the pi bond. That should generate this tetrahedral intermediate. Now we can judge what happens next with our same familiar consideration. This is the hydrogen that was already there. This is the hydrogen that got delivered in the nucleophile. We ask ourselves, do we have a good leaving group relative to a negatively charged oxygen? We do not. That means we are stuck until aqueous workup. So I'll just draw that here. AQ stands for aqueous workup. That's going to involve protonating the oxygen that's negatively charged oxygen from the tetrahedral intermediate, and that gives you this product which happens to be a primary alcohol. What I've just shown you is a reduction reaction because we've increased the number of carbon-hydrogen bonds in our molecule. We've reduced our molecule from an aldehyde to an alcohol. We would call this an example of a nucleophilic addition reaction because look at what just got added to the molecule, the nucleophile, and then the hydrogen from the aqueous workup. So that's an addition product. Now, you do not need to memorize that aldehydes react with sodium borohydride to give me primary alcohols. You can if you like chanting, but it would be pointless because you can figure it out if you understand these mechanistic issues that we've talked about. Let's do an example with lithium aluminum hydride. I might have chosen lithium aluminum hydride here. I could use those interchangeably. That's just fine. For variety, I'm going to draw a different molecule, and we're going to use, it's a ketone. We're gonna use lithium aluminum hydride with the ketone. I'm not trying to communicate that you use one for one and the other for the other. You can use sodium borohydride and lithium aluminum hydride interchangeably for aldehydes and ketones. For other types of carbonyl compounds, well, we're gonna have to see because there are some important considerations there. To draw a mechanism with a lithium aluminum hydride, you draw the aluminum hydride portion like this. As with the borohydride portion, you show H- leaving and attacking the pi star to break the carbon-oxygen pi bond to give a tetrahedral intermediate. That nucleophilic addition step we consider is reasonable because H- should be a good enough nucleophile to generate a negatively charged oxygen. Let's see, our Y group was this methyl, and the nucleophile that got delivered was a hydrogen. Let's see. I'll just draw it here. And then we would ask, do we have a good leaving group? Let's see, purple is for our nucleophile, yellow is for our prospective leaving group. No, relative to a negatively charged oxygen, CH3- is a terrible leaving group, so is H-. So there we are stuck. How on earth did that turn? Goodness. All right. We are stuck until aqueous workup, whereupon we would get the product shown here. Now, why don't I see a handout in the audience? What did I do wrong? Somebody should be uncomfortable with what I did. Yes?
Isn't aluminum hydride strong enough to kick off the CH3?
Lithium aluminum hydride is strong enough to generate O-. That's the correct comparison. The next comparison is O- strong enough to kick off CH3? And the answer is no. Yeah. Even if you were going to ask, can H- act as a nucleophile to kick off CH3-? Those are both terrible leaving groups, so no. Okay, there's another issue that should have made you uncomfortable. Go ahead.
Shouldn't this be racemic?
Shouldn't what be racemic?
The product.
Shouldn't the product be racemic? Yeah, why did I show dashes and wedges there? Because it's a stereo center, right? I now have 4 different things attached to that carbon. It's a stereo center, but my starting material was not chiral, and my reagent, which is lithium aluminum hydride, is also not chiral. Therefore, if I make a stereo center in this reaction, I must get both configurations. Now notice the product that I drew shows the hydride having been delivered from the bottom face of the carbonyl. But remember what I told you about the pi star. See, this is why you need to know the orbital stuff. The pi star, which we drew on the carbonyl like this, there's a lobe above the plane of the page on the carbonyl carbon and a lobe below the plane of the page. The 2 faces of the carbonyl are identical. The carbonyl is flat. You can attack the pi star from the top or the bottom. So, if you make a stereo center and your starting material is not chiral and your reagent is not chiral and the 2 faces of the carbonyl are identical, you must get both stereochemistries. You must get both configurations. Now, the way you can draw this, I'll give you a few options. One of them, which is more time intensive, is to do this and just draw the other stereoisomer, the other enantiomer. Or if you're in a hurry, you can draw the one enantiomer and then in parentheses use a ± symbol, which communicates both enantiomers. Or somebody in the 9 o'clock hour is like, well, can I just draw the one and then write plus enantiomer? I'm like, yes, if you want to write out plus enantiomer instead of that lovely little ± in parentheses. Or alternatively, you can just draw the molecule like this and fail to use dashes or wedges. But you got to be smart when doing that. When you draw it like that, you're not communicating that all of those bonds between this carbon and the other groups are all in the plane of the page, like you've invented some weird new hybridization of carbon. Instead, you got to be smart enough to realize, okay, 4 things attached to a carbon, that's sp3 hybridized, it's tetrahedral, one should be a dash, the other should be a wedge. They're not showing it because they mean I got both configurations. Does that make sense? All of those are acceptable. You will probably see all of those answers in keys to problem sets or in the back of the book. You got to be comfortable with all of them. All right. Other questions? While we're on the subject of chirality in products, I want to show you what nature's hydride delivery reagent is. Nature uses enzymes and a cofactor called NADH, and sometimes another one called FADH2, but mostly NADH, to deliver hydrides. Nature doesn't use NABH4 or or Li, lithium aluminum hydride. Instead, it uses something called NADH. That stands for nicotinamide adenine dinucleotide, and you get at least part of this from vitamin B3. I'm going to draw this for you, and we'll start with the part of the molecule that matters most, and that's the nicotinamide portion. That's where the N comes from in NADH. You got 2 hydrogens on this sp2 hybridized carbon in this ring, and that's the important part of the molecule. Then there's more. There's always more in biology that you don't want to know, but that I'm going to show you anyway. Those should be wedges. A couple of phosphate groups. This is where the dinucleotide part comes from. Come on, keep up. And then there's this portion. This portion is where the A in NADH comes from. What we're actually drawing here is the adenine base of NADH. I'm sorry, folks, if you're worried about that, this semester is going to get so much worse for you before it gets better. Now, the question that I presume that you're muttering about to each other is, does he really expect us to memorize all of that? The answer is no. Though you should be familiar enough with it that you don't look at it and have no idea what it even is. I've highlighted in orange the important part of the molecule. This is the N. The A comes from this portion, which is adenine. The D comes from this portion, which is a dinucleotide. And the H comes from one of these 2 hydrogens on the sp3 hybridized carbon in this ring. We're going to talk about why this is a hydride delivery reagent later. We need to do some more background before we can get to that point. But I wanted to show you an example of this being a hydride delivery reagent, putting it into action. The molecule that it's going to deliver its hydride to is pyruvate. Pyruvate has multiple functional groups. There's a ketone and a carboxylate. What I just told you up here is that ketones are more reactive than carboxylates. So you expect pyruvate to be electrophilic at the carbonyl carbon. The hydride delivery step comes as the enzyme delivers a hydride to the carbonyl carbon to give a tetrahedral intermediate. The enzyme is called lactate dehydrogenase. This enzyme is named actually for the product of the reaction, and we'll talk more about enzyme names another time. But the enzyme is chiral, and so it directs the hydride to be delivered selectively to the top face of this carbonyl compound. Then we're stuck at this tetrahedral intermediate with no good leaving group, And so then the negatively charged oxygen picks up a proton from some source, possibly water, possibly a group in the enzyme active site. And the product is one and only one stereoisomer of this molecule, which happens to be called L-lactate. So you've probably heard about this reaction. This happens when your body has an excess of pyruvate and an excess of NADH and needs to do something to carry things forward, and so it will reduce pyruvate to lactate. This happens under conditions like anaerobic respiration. Pyruvate is a product of glycolysis. We'll talk about that later. Yeah, go ahead.
Does this have like a chiral split, like, or is it just L?
I'm sorry, does it have, I missed the question, does it have a chiral what?
Does it have like an enantiomer, like autolactate?
Right, there is another enantiomer, but only this one is formed by the enzyme. Why? Because the enzyme is chiral. It can block one face of the ketone so that the hydride only gets added to the top. Yes?
Why would I guess like the electron densities be closer to the hydrogen instead of rather than to the carbon?
So why, the question is basically why can this hydrogen act as a nucleophile? You've never seen anything like that before, a hydrogen leaving for a carbon. I'm going to punt on this other than to give you the really short answer, which is the thing that's left after that hydride leaves looks like this.
Oh, because it's really stable.
And it has a positive charge on the nitrogen, but this intermediate has a special stability called aromaticity, which we will not talk about for several more chapters. But that's what makes it possible for NADH to lose a hydride. Yeah?
So the oxygen can't have a wedge, it'll always be dashed when the...
That's right. Now there's nothing for you to memorize here or predict because it's the enzyme that controls that stereochemistry. I haven't told you anything about the structure of the enzyme. If we looked it up and looked at the structure, what you would see is the enzyme holds on to pyruvate and also holds NADH above pyruvate so that the hydride has to get delivered from that face. There's nothing for you to learn to predict here other than to have the idea that a chiral enzyme can literally give you just one enantiomer as a product. Yeah. Such types of reactions are called enantioselective. Okay. Yes? Lithium aluminum hydride is not a good acid. You need an acid that has acidic protons. And as I told you with lithium aluminum hydride, those protons are not electron poor, they're actually electron rich. So no, you can't use it as an acid. You do have to have aqueous workup. Good. Okay, I need the last 2 minutes because otherwise we're going to fall too far behind. What I want to show you now is what happens to something like an acid chloride when you use lithium aluminum hydride with it. This is an important point. Lithium aluminum hydride attacks the carbonyl carbon to give you a tetrahedral intermediate. That's not new. Unlike with the aldehyde or the ketone though, you get to that stage and you do have a good leaving group relative to the negatively charged oxygen. So electrons on the oxygen kick down and chloride leaves to give you this aldehyde. Now the problem with that is that the aldehyde is just as reactive as the acid chloride starting material. Remember, they're both among the list of most reactive starting materials. And so it turns out that we can't stop at this stage, that the aldehyde will start to react with lithium aluminum hydride 2 to give you another tetrahedral intermediate. Now though, you don't have any good leaving groups, so you wait until the reaction's done, then you do aqueous workup, and you get this primary alcohol product. The point is that with lithium aluminum hydride, you cannot stop at the aldehyde. You keep going on and reacting to get to the alcohol. And that, unfortunately, we're out of time. I know you have questions about that, and I know what they are. So we're going to pick up with that at the very beginning of class next time. All right, see you Wednesday.